Hello and welcome everybody to the Distributed Machine Learning workshop. This is the third iteration. The workshop started in 2020. Both me and Stefanos Laskaridis, we were both working at Samsung AI. To give you a bit of context, we were a bit frustrated at the lack of specialized machine learning systems conferences out there. Let me get out of this. And basically, we decided to create a venue where AI, distributed systems, and networks people could come together to discuss their works. Around the second iteration of the Distributed ML workshop, we invited John Crocroft. For the few of you that might not know him, he's one of the pillars of the communication systems research community, a professor at the University of Cambridge, and also a chair at the Alan Turing Institute. And he has been doing a lot of work in the intersection of networks and machine learning in the recent years. Furthermore, I'm very proud to have Lydia Shannon Angley this year as chairs for the workshop. They have extensive contributions to the machine learning community. Lydia is an associate professor at TU Delft, where she's leading the Distributed Learning Systems Lab, while Angley is a research associate at Qualcomm AI in California. And they've both been providing significant contributions in the areas of big data, machine learning, federated learning, and privacy research. As you all know, machine learning has been taking the performance lead in many applications, from things like image-to-speech recognition all the way to recommendation systems. The applications of machine learning range from things like simple sensor automation and photo filters, all the way to smart cars and smart assistants. Each one of these scenarios presents very different challenges. For example, if you consider smart cars and drones, they have stricter runtime requirements in terms of latency, while smartphone or medical applications tend to have other challenges like scale, data imbalance, fairness, explainability, privacy constraints, and so on. Nonetheless, we believe that the best is still to come. And as we scale the machine learning applications to more complex and challenging scenarios, like smart cities, enterprises, and organizations. Not only machine learning is becoming more widely adopted, but it is also becoming ubiquitous. Nowadays, machine learning models are being trained and run everywhere, all the way from smaller scale microcontrollers and phones that are now starting to integrate neural processing units, but they also have other restrictions like the small form factor that ends up having restrictions in terms of memory, in terms of battery capacity, in terms of also compute capabilities. Then you start having devices like the NVIDIA Jetson that already provides high performance sensor cores for machine learning and is often deployed at the edge. That already starts having a very good package in terms of basically having a small form factor and a good compute power performance. Then in the case of smart cars, they need high compute to run machine learning vision tasks. And then you have things like the network edge that we're starting to see technologies like network function virtualization, mobile edge computing being adopted by ISPs that are bringing the compute closer to where it is needed. Okay, and even things like smart NICs that are already able to run machine learning algorithms. And of course, on the more compute-intensive side, we have the cloud, where more and more GPU offerings have been appearing in later years. And we're also seeing that AI-related semiconductors are growing at 5 times the pace of non-AI applications. Now, in terms of challenges, while machine learning applications are becoming more complex, so are their models. The increase in accuracy often comes at the cost of floating point operations, okay? And this reflects both in training and inference time. If you look at the left, you will see basically that the training time has been growing considerably over the last years. The most performant models come at a prohibitively high cloud compute cost and time for small and medium companies. On the right side, you will see that the high accuracy has been elusive for the recent smartphones. In this case, it's S9. It's not that recent, but you can see that basically these devices, they struggle to achieve a good inference per second, and at the same time, they suffer from other things like thermal throttling or even degraded battery life. Another interesting dimension to this problem is that we're starting to see the emergence of network technologies like 5G, where instead of the hundreds of milliseconds that we used to have in the past, we start aiming towards like a 1 millisecond latency to the base station. And what this means is that with technologies like mobile edge computing and NFV that are bringing the computation closer to the base stations of ISPs, we're seeing more and more use cases for scenarios of offloading computation to the edge. Another challenge in distributed machine learning is the fact that compute and data are scattered, okay? So there is no single optimal compute location. And if you think about it, machine learning models, generalization depends on how representative your training data is, right? And with models being deployed in the edge and data being generated in this device under heterogeneous environments and different users, this data is very useful, if not a necessity, to reduce the biases and also to attain high accuracy. Now, if you think about the scenario of smart assistants, for example, you require a quite significant amount of speech samples in order to be able to generalize to a wide range of speakers, for example. And often when you have limited data sets, you also result in biases. While historically we've been training machine learning models in the cloud, where the compute is elastic, obviously, it often comes at the cost of reduced privacy because data is being generated in your devices. You need to share the devices with the cloud in order to train models. Another very promising direction that we're seeing, and that we will have the topic here as well, is the topic of federated learning, where basically models are being trained on the edge devices, and then only the models are shared with the cloud, where we aggregate and build a global model. Now, this comes also with challenges, things like the fact that the edge devices have limited resources, network latency, data imbalance, and independence, device availability, and so on, right? Another interesting thing is that because the edge devices have quite low compute, we start seeing other scenarios like sharing compute with proximate devices, either it be in local networks or in compute nodes at the network edge, right? And here you start seeing other trade-offs between faster compute and communication overhead. Another very interesting scenario is actually context sharing, in the sense that you can have different inputs coming from different sensors from different devices, or you can have cross-modality model ensembles where you have multiple network outputs being used for a combined inference. But all of these scenarios, they also bring new challenges, things like having to do trusted zones for collaboration, hardware resource allocation, or even network sharing. Now, all of these challenges together, to be tackled, they need innovation at all the levels of the machine learning stack. Starting from machine learning models and techniques, we've seen knowledge distillation, for example, to train smaller models. We've seen techniques to reduce computation memory requirements, such as pruning, early exiting, quantization, and so on. On the forefront of machine learning frameworks, we're seeing optimized kernels that execute faster, parallelism, reduced memory consumption, and also novel scenarios like federated learning, neural architecture search, hyperparameter tuning, and so on. On the OS and networks, we're seeing a lot of things from RDMA to be able to access directly the GPU, machine learning specific compression and encryption, GPU virtualization, things like 5G, mobile edge computing that are enabling also latency critical applications. On the hardware side, on the data center, we're seeing domain-specific machine learning accelerators, GPU designs with tensor cores. On the mobile side, things like neural processing units. And on embedded devices, we're seeing a lot of new deep learning optimized platforms, such as the NVIDIA Jetson, and even devices that consume only 1 watt of energy, like the compute stick from Intel. Now, distributed ML, it's basically either it be for training or inference, or across the cloud infrastructure, or with scattered devices across the edge, is a challenging domain of machine learning research where all these innovations come together, okay? This year in particular, we had a focus on robust and sustainable distributed machine learning. In distributed environments, obviously, these are more susceptible to adversarial attacks, and we need to be able to sustain model performance even in the presence of corrupted data or outliers. And we also are focusing more on sustainable AI, where we see innovations like hardware innovation, energy-aware sharing, multi-communication channel optimizations, and so on. So to address all of these challenges and novel use cases, we created a distributed machine learning workshop. This year we had a very competitive acceptance rate of 35%. We have 6 papers that are going to be presented today. I would like also to thank our TPC reviewers for the awesome reviews from the papers. In the session, we will have 3 parts. We will start with delving at the topics of distributed learning and inference in novel scenarios, with a keynote on programmable networks for deep learning and then we will go into a session about machine learning and the transit resources. We then will focus on the topic of federated learning, okay, with things such as normalization and predicting client benefit and contribution in federated learning. In our third part, we will have a keynote on scalable and resource efficiency in machine learning, followed by very relevant topics on efficient and robust machine learning deployments. And finally, we will conclude with a panel session touching upon many of these topics with very prominent researchers. So stay tuned until the end for this awesome discussion. So yeah, that's it. Thank you all very much for attending. I will now pass the stage to Marco Canini,